against the expected frequency. So I'm going to ask for the expected frequencies to actually be printed out here. So I hit continue here. So let me just say that again. I click on cells. I'm interested in what the expected frequency should be. So I'm going to hit under counts for them to be printed out in the table. I'm going to hit continue. From a statistics perspective, I'm interested in the chi-squared test of independence. So when I click on statistics, this little pop-up pops up and I'm just going to tick chi-squared here to indicate that I want SPSS to perform the chi-squared test of independence. And that's effectively it. So let me hit continue here, let me hit OK, and what we get here is we get a lot of output. Okay, we have the case summary table. There was 173 observations in total. There's no missing values, so the total valid observations is 100. There was 173 in total. There was no missing values, and so the valid number of observations being fed into this analysis is 173 observations across gender and salary categories. The actual cross tabulation is done here for us. So SPSS takes care and actually counts how many people are within the particular categories. So you can actually see from a gender perspective, we have two categories, male and female. From a salary band perspective, we have three categories, the first, the second, and the third. And then what it's done here is it's counted in my columns how many males there are in the 20 to 60 category, which there were 60. How many males are in the 60 to 100 category? There was 28. How many males are in the 100 to 140 category? There was 17. Okay, so the question is, are these, I suppose, let's say, observed frequencies what we'd expect if there was independence between a gender and salary band? And there's a formula for doing that calculation, and I have a video online on YouTube as well on how to undertake a chi-squared test of independence by hand. But if we did it by hand, what SPSS is saying is that of the 105 males, we'd expect to see 60.7 males in the first category. So we've seen 60, so that seems to be balanced enough. We'd expect to see 32 in the second category. We've seen 28, so that's pretty close, albeit we'd expect to see more males. And finally, we'd expect to see 11.5 males in the third category. We're seeing 17. Okay, so we're seeing more males in the higher salary bands than what we'd expect. Okay. In relation to the females, we've got 40 females, okay, in the first category. We'd expect to see 39.3, so that's relatively balanced. We'd also expect to see 26, we see 26 females. We have observed frequency of 26 females in the second category. We'd expect to see 21. And finally, in the third category, are observed, we only have 2 females in the third salary band. We'd expect to see 7.5 females if the categories on gender were independent of the categories on salary band. Right? But anyway, what we're really interested in is this output here, which is the chi-square test of independence. We're interested in the Pearson calculation. The actual chi-squared value from that calculation is 8.386. And let's just keep in mind is that a chi-square value of 0 would indicate that there was no difference between the observed and the expected. And we've got a pretty big chi-squared here, but we also need to take into consideration the degrees of freedom. That's how many levels of measurement there are associated with the gender cross salary band variables. Gender, there's 2 categories. Salary band, there's 3 categories. The degrees of freedom of a chi-square test is the number of categories minus 1. So in gender's case, it's 2 minus 1, which gives us 1, multiplied by the number of categories on salary band is 3 minus 1. The degrees of freedom there, which gives us 2. So we have 1 times 2 gives us 2, which is what we have here, 2 degrees of freedom. But more importantly, the actual p-value associated with this test is listed here under asymptotic significance, two-sided. Okay? And what we have here is that the p-value is 0.015. Okay? So keep in mind, if the p is low, the null must go. Let's assuming, well, we'd run our tests at the 5% significance level, and what we see here is that the actual probability of observing this test statistic is 0.015 if the null was in fact true. So it's a very, very small probability of observing the data that we observed conditioned on the null hypothesis. So in this case, you can clearly see the p is low, it's 0.015, it's less than our significance of our test, and hence we are rejecting the null hypothesis. in favour of the alternative. And the alternative is that there's a dependence between the categories associated with the variables. In other words, salary bands are actually dependent on your gender. Okay? So, although this was fictitious data, this is, I think, an interesting example of the way you could test within your organisation if there is evidence to suggest that there's a different number of males compared to females, or different proportion of males compared to females at each of the salary band levels, and more importantly, that females don't seem to be progressing through to the upper salary bands. And this is an example test here with fictitious data that supports that. There is evidence to suggest that within this organisation, that salary band is actually dependent on gender and not the other way around. Okay guys, once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. I hope that this video was intuitive, and more importantly, I do hope that was helpful for you, and thanks for watching. Okay, bye bye.